So our review of trig stuff. We started with this unit circle business in trig last year. All of us had that at some point. Just going around and trying to remember some of this stuff. We started here with 0 degrees and we went counterclockwise around the circle. From there, if we skip this middle one in every quadrant, it goes up by 30 degrees. So if you count with me, it just goes 30 degrees, skip the middle one, 60 degrees, keep going, 90 degrees, 120, I don't know why I went to 2, 120, skip the middle, 150, 180, 210, 240, 270, 300, and 330, and then one full rotation around was 360, yes? Okay. Given that information, does anyone remember how we found that middle one?
15.
It's 15 between the two in the middle, or 45 between 0 and 90, right? Either way you want to think about it. So this is 45 degrees. Halfway between 90 and 180 was 135. Halfway between 210 and 240 was 225. And halfway between 300 and 330 was 315. Now, the degrees always came easier to us than the radians did, if you remember the pi ones. Okay?
I don't know what a radian is.
Oh, wow.
All right, so.
You're going a long way to go, buddy.
Well, this is why we are reviewing this today. It's okay. We'll be fine.
I don't either.
Okay?
You got a long way to go.
All right, so let's go back through the radians that go with each of these. The radians were the ones in terms of pi, and they were fractions. So it started with 0 radians, and then 30 degrees was the same as pi over 6. The halfway ones were all over 4, so this was pi over 4, and this was pi over 3. Top was pi over 2. Now, I know I taught my people the patterns to the fractions. So there's reflections here. Like across from the pi over 6 reflecting over at 150. This is also going to be over 6. This is also going to be over 6. This is also going to be over 6. The middle ones are all going to be over 4, right? Do we recall this a little bit? These are over 4. These are over 4. And that means that the leftover ones, the 120, 240, 300, are all over what? 3, because they're the reflections of the other ones, right? Over 3, over 3, correct? If you wanted to, you could have memorized these. Some people treat them differently. Some of them count up by pi over 6s every time. In the second quadrant, it was 2 pi over 3, 3 pi over 4, 5 pi over 6. Some people remember those because each of those numbers are 1 less than the denominator. So 2 over 3, 3 over 4, 5 over 6. 180 was the same as pi. In the third quadrant, it goes 7 pi over 6, 5 pi over 4, 4 pi over 3. This is a good reference to keep. 270 was 3 pi over 2. I didn't write that one down. And then the last quadrant, 300 was 5 pi over 3, 7 pi over 4, and 11 pi over 6. Ending at 360 was 2 pi. Okay. So we're going to kind of reference this going back and forth between the back of this page to practice some of the trig values. Once we dealt with the unit circle there, we kind of built the chart above and the sine, cosine, tangent values for each of those degrees. So the first thing I want you to do is across the top of that table, next to the 0 degrees, 30 degrees, 45, so on, write the corresponding radians in the boxes with them. So 0 degrees is the same as 0 radians. 30 degrees is the same as how many? pi over 6. So fill those in across the top of the table there. I'm just going to leave this here for a second in case.
Wait, how do we know which one it is for the other ones?
We'll talk about it.
Just do the top row?
Right now, just do the top row. Yep.
Are we gonna have chart quizzes?
Probably. I know. Easy 100 quiz thing. Once you memorize it again. Okay, so we filled in the corresponding radians to go with each of these. This was pi over 6, pi over 4, pi over 3, pi over 2. Now, when we built this chart to begin with, I'm not going through the entire process of where these came from.
Wait, were we supposed to put that up there in the box?
Right in there. Do you need whiteout already, Jackson?
Yes, I need white out. I'll go grab it.
All right. Here.
Jackson doesn't. Because I don't use pencil.
All right, real quick. When we built the sine, cosine, tangent values in this chart, we referenced the special triangles from geometry that were 30, 60, 90 triangles, 45, 45, 90 triangles. At some point, you built that entire understanding. I am not going to go back through that right now because we don't actually need to do that again. Okay? So, what we did when we found these. Is it out now? You broke it? It's okay. It might be out already. When we built these, we
I'll just cross
first.
it out with my fingers.
Here, try this one.
Oh,
I have other ones. All right. When we built these, we said, okay, our sine values start at 0.
Oh.
And our sine values go 0 to 1 in increasing numbers.
Yeah, same thing.
Okay, you don't know how to use these then.
I don't know how to use this. I'm just
Special.
gonna cross it out. I'm gonna use white out. So how do you put Jackson, dude? That's great. That's great.
All right. When we built these, we went from 0 to 1.
So hard.
Okay, we said the sine at 30 degrees was 1/2. This one was root 2 over 2. This one's root 3 over 2. When I taught these to my classes, we talked about there's kind of a pattern to those 5 values. So the main thing is being able to get those 5 down, because then to fill the other 2 rows in, there's tricks to it. Okay? So what I told mine, that this, every single one of these, I can make this root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. So there's like, if you just make everything over 2 and reduce it, that's how you get those numbers. Root 0 is just 0. Over 2 is just 0.
I'm sorry, that just really.
Okay, well then don't worry about it. If that confused you, just memorize the first 5. Okay, it's gone. All right, anyone remember what you do for the cosine values?
You flip them.
Take all 5 and reverse them. Okay?
Yeah.
So you take 1 and go down to 0 and reverse the order on them. So it goes root 3 over 2, root 2 over 2, 1/2. So if you know the first 5, you flip them for the second 5. Anyone remember how you find the third
Flip them
line?
upside down.
You take the
You just go to the bottom.
Top divided by bottom.
Oh,
Yep.
yeah, that's what I meant.
Okay, so I'm going to do 0 divided by 1.
0.
0. Okay.
You got to play.
1 divided by root 3.
1 over square root of 3.
Root 2 divided by root 2. 1. Root 3 divided by 1.
Root 3.
1 divided by 0.
Undefined.
Undefined. Good.
Oh, God.
All right.
Get them, Jake.
You remember more of that than I expected. That's good.
Thank you.
All right. So, with those, we are going to be able to find sine, cosine, tangent values like we have on the back. So what I'm going to do, because that's the one thing I didn't think through with this, you don't really want to be flipping back and forth here. Okay, so I'm going to leave my chart here. Okay, everyone else flip to the back. Well, before we do that, let's fill in the plus minus chart. Okay? So, the plus minus chart just tells you where things are positive and where things are negative. In the first quadrant, what's true about sine, cosine, and tangent? They are all what? Positive. So put plus, plus, plus in the first quadrant. Okay? Okay? So in the first quadrant, we are just putting plus, plus, plus. Everything is positive in the first quadrant. If it helps you to remember, sine is associated with y, cosine is associated with x. So now when we switch to the second quadrant, which one is negative?
Cosine.
Cosine is negative, which also makes tangent negative.
Money.
Sine stays positive. Now, I'm not going to erase mine because I want to leave this chart up here for y'all. In the third quadrant, what's true? Sine and cosine are negative, which makes tangent positive. Good. So it's going to be minus, minus, plus. In the fourth quadrant,
Minus plus minus.
minus, plus, minus. Yes. There you go.
It's your world, Jackson. We're
I'm
just
fully
living in
subverting
it.
to my bag.
All right. So now we are all flipping to the back of this page. Okay, I'm going to leave my chart here for you and walk you through the first one. Or at least one of each type. Yes?
Yes.
All right.
Oh, God.
Oh.
Okay, this is not as hard as you want to think it is. So just settle with me for a minute. Okay? We don't always remember these.
One half.
All right, so walking slowly through this first question. First question is sine of 120.
One half.
Okay, here is my thought process. Each of these angles have a reference angle. Okay? Reference angles are what we're going to use these for at the top. Okay? So when I think about 120, I would not be drawing all of this out. This is, I'm doing it in my head, but I'm just going to kind of show you for the first one. Where is 120 in our unit circle picture?
Top left.
Okay, it's the top left. It's right here. Its reference angle alpha is the difference between 120 and 180. What's the difference between? 60. That means when I want to answer sine of 120, I look at 60 because of the reference angle.
So is it going to be square root of
So
3
what's
over
the
2?
sine at 60?
No, it's
Square root of 3 over 2.
It's square root of 3 over 2, and then the last thing I check is my plus minus chart. In the second quadrant, sine should be what? Positive. Okay? Should we do another one together? Okay.
No,
Cos-
don't worry, I got this now.
Okay, second one. Cosine of 150. So the first thing, this time I'm not going to draw it. I'm going to think 150 is in second quadrant. How close is 150 to 180? 30. So that means I'm going to look at 30. I'm going to look at the cosine of 30. What's the cosine of 30? Root 3 over 2. And then I'm going to look at my plus minus chart. In second quadrant where 150 is, what should cosine be? Negative. Okay? All right. Let us just take a moment. We're just going to work through 9 right now. I did 1 and 2 with you. We're just going to work through 9 right now. Using that same process, talk to the people around
Is there any way you
you.
can put the circle on the board so we don't have to flip pages back?
Do you want the circle or the chart?
Oh, actually, we'll need both. So,
I know. I can't get both up there right now.
Why is it where you can see both?
I can't because the writing's kind of over top of it.
Oh. Oh. We'll just take that. That's perfect.
All right,
You
I'll
can see
leave
the
that
fingers,
and you
too.
can. I feel like as you think about the circle, it's less needed than the chart. But I can kind of picture where the angles are. All right, so we're
Can you
working
just draw it a
through
little bit so I can see
question
the
9.
negatives on the side- on the,
I actually can't
Oh, okay. It's fine.
because
I'll write
it's.
them down. It's
But
not-
I can write it here. How would that be?
Oh, I mean, I wrote it down. I want to save you some time, but
Alright.
on the test, you know,
That was so innovative.
I wrote that over right there.
Thank you.
And then after you use it on the test, you go, oh, wait, so they erase that? 30 times.
There you go.
That's what else.
That help?
Oh, thank you.
All right, so we're working through 9 on the back right now. Then we'll talk radians. Okay.
Okay, you know why both of those say no right there?
Why?
Because I love you.
Oh, good. I miss this class so much.
What's the z that goes to 0 to 180?
All right, so we're working through question 9, and then I will go through answers on those. There we go. Fixed it. So for question 10, sine of 3 pi over 4, let me write it up here. First, I just need to know what quadrant 3 pi over 4 is in. Which one?
The top left.
Second. That's what's going to tell me positive or negative, right? What is the reference angle automatically for 3 pi over 4? It's automatically pi over 4. I don't have to think about that because they share the denominators, okay? So if you're given a pi over 4, it's a pi over 4. If you're given a pi over 3, it's a pi over 3. It's automatically that, okay? So what is the sign at pi over 4? Root 2 over 2, and then I only check in quadrant 2, should sign be positive or negative? Positive. Let's try that again for question 11. Okay, so 11. 11 is cosine of 2 pi over 3. What's the automatic reference angle for this?
Pi over 3.
Pi over 3. What's the cosine?
1 over 2.
1 over 2.
But
Okay, then I have to check where is 2 pi over 3.
second quadrant.
Second quadrant, and I look at my chart. Should cosine be positive or negative?
Negative.
Negative. Okay? So we're going to do the same thing. Take about 5 minutes. Finish out through 18. Okay? Finish out through 18. We all doing okay online? Remembering this fun? All right, I'm going to see if I... All right, so given what we don't know, because most of us don't remember anything about limits, first things is what is a limit in general, okay? So to see what a limit is, we're going to take a look at a graph. If you want to, you may pull your calculator out and graph that function that you are given. If not, I will just graph it myself and draw a graph for you so you know what we're looking at, okay? So we are going to take a look at x cubed minus 1 over x minus 1. Okay, this is a rational function. You graph these in pre-calc sometime. If you take a look at what this looks like, it ends up looking like, if this works, rather like a quadratic. Okay, so if I graphed this function, it crosses the y-axis right here at 1, dips down, and looks at that. Okay, so that's kind of what our function looks like. Our question is what happens to the function at x equals 1. Okay, if I just draw that, and I'm going to draw a little bit of a better sketch here in just a second. This is, if this freezes on me again, I'm going to throw something. If I graph this, I can see that it has a point at 0, 1. I can see it has a point at 2, 7. 1, 2, 3, 4, 5, 6, 7. Okay. And I can see it has a point at negative 1, 1. And like I said, it's that U shape that looks like this. Okay. So looking at the graph, could you estimate what it looks like the graph is touching at x equals 1? Like if I asked you for an ordered pair on my graph, at 1, what do you think the y value would be? 2. You'd guess at 2. Yeah? Now, let's talk about what it actually is. If you want to find a y value, we don't usually estimate off the graph, but we do. We usually plug it in, right? So let's just try that real quick. F of 1. Rather than guessing, let's actually find it. So I'm going to plug in 1 for all of my x's. What am I going to get back out? 0 over 0. Anyone know what that actually is? It's not actually 0.
Undefined.
It's undefined. Okay? Anytime You have 0 on the bottom of a fraction. You get undefined back out. So officially from that equation, is there a value of y when x equals 1? No, there's not officially. Unofficially, we can find from the graph what it looks like it's getting close to. Okay? When you told me that on my graph it looks like it's about 2, that is what a limit is. Okay? A limit is an approximation of a y value, especially when there's a problem in the equation. So this one, there's a problem at 1. We can't actually plug in 1. So a limit is saying, if there's not actually a value, can I still predict what it's getting close to? Yeah, I can predict that it's getting close to 2. That's what I would guess. That's what the limit is. Okay? Now, there's a lot of different ways to find out what it's approaching. You took a good guess off of my graph. I'm not a great drawer, so maybe that's not a great guess. So one way is to do what you see below. This is kind of the most painful way. Okay? We tried plugging in 1, and we got out undefined. But what you can do is plug in decimals on either side of 1 and see what they're getting closer and closer and closer to. This is kind of a painful method. I'm not going to make you do this more than like 2 times because it's not the best way to do this. So we can approximate it if we plug in numbers. I'll just do a couple of these. So if I take my calculator, and I'm just going to plug in the 2 on either side. We don't even need that many, right? The closer ones will help us more. So I'm going to start by plugging in 0.99. So I'm going to do 0.99 cubed minus 1 over 0.99 minus 1. That gives me 2.9701. Lovely number. Let's try the same thing with 0.999 and see if we can get a better approximation. Oops, not there. All right, let's try here. All right, so if I plug in 0.999, my calculator tells me 2.997. I'm going to plug in the 2 on the other side, too, to see what we get. Let's see if I plug in 1.01 for both x's. So if I do that, I get 3.0301. Let's try the one closest as well. All right, so like I said, this is not the fastest or nicest way of finding a limit, but we can use it. So if you have no better method, you can plug in numbers real close on either side of 1. Even though we actually get undefined when we plug in 1, if you look at those numbers as you kind of come in closer from either side, what do both of those numbers on either side look like they're getting closer to right here? 3. So if you didn't know that you couldn't plug in 1, you would say 3. That's the limit. That's the limit. So even though there is nothing on the graph at that point, even though officially right here there's a hole in the graph, you are telling me that the graph looks like it's getting closer to 3 regardless. Right? That's what the limit is. Okay? So it's an approximation of the y value when there is no y value. Yes, sir?
So could you just do like the 0.99 and the 1.001?
If that gives you enough to figure it out, yes. So that is the nice thing about limits. If you can figure it out without doing all the stuff, do it. You're just trying to figure it out. If you can figure it out from the graph, great. Perfect. There's going to be other ways to do that because I don't know about you, but I'm not a plug-in random number person. I don't like that. So we're going to spend a lot of time using algebra to do it, which is actually easier in my book. Okay? But that is one method of finding an approximation to that. I really don't think we need to do the table stuff too much. Anyone agree with me on that?
Is that what that is?
That's the table, yeah. It's just plugging in random numbers.
I don't really want to do that.
Okay.
It's so pointless, let's just cut it out of the lesson.
All I want you to know is that you can use that if you need it. Okay?
Will you give us the numbers to plug in, or is it going to be pretty much the same things that we type in every time?
It depends on what the limit's near. So let's just talk about that. Let's not fill in the table, but let's just say if I had to do it, what numbers would I use? Okay, so if we want to approximate the limit near 0, okay, so 0 is kind of our middle number here. We can't actually plug in 0. If I tried it, I would get 0 over 0. So what are some good numbers on either side of 0? What's slightly larger than 0?
0.001.
0.001. A little bit further away would be 0.01. A little further away would be 0.1. What about on the negative side?
Negative 0.001.
Okay. Negative 0.01.
Negative 0.1.
Okay. And those are the numbers you would plug in and just see if it worked. I wouldn't worry about it too much beyond that. Okay? All right. Sometimes you can find a limit like we did in the first one. So there was no value when we plugged in 1, but we could figure out what it was getting closer and closer and closer to as we kind of drew in on that graph. Sometimes you can't find limits. So let's take a look at one that doesn't exist. Okay? This is what we called a piecewise function. Okay? Just to kind of give you a quick graph of what this would look like. This one says it's defined as y equals 1 when x is not equal to 2. What kind of graph is y equals 1? It's a horizontal line, right? So it's a horizontal line like that for everywhere except x equals 2. So that means at x equals 2, there's a hole in the graph right there. What does it say then in the second line that it's equal to when x equals 2? 0. Okay. Now, the limit is the approximation or what the graph is getting closer and closer and closer to as you kind of track in from the sides. So if I looked at this, what I would do, and I have to kind of draw it up here rather than I usually gesture up at the front, but my online people can't see me. So what I would do is literally track in towards my x value of 2. Okay? And if I tracked in, not knowing what the rest of the graph would look like, what would you say, what would you guess the y value would be at 2? I would guess it's 1, right? Because it's tracking along at 1, it's tracking along at 1, and then bam, all of a sudden you hit 1 and it's not 1, right? Or hit 2 and it's not 1, okay? That doesn't matter, okay? If I asked you the limit as x approaches 2 of this function, you would still tell me the limit is 1 because the graph is tracking towards 1, okay? So there is a difference between a limit, so it's an approximation of what the graph is doing, versus f of 2. What is f of 2 asking me? What's the value specifically at 2? So at 2, the value is 0 because that's where the closed dot is. So the limit is what you are approximating, what the behavior of the graph is telling you should happen, where the f of 2 is the instantaneous right at this moment what is happening. Okay? So the limit is more looking at predictions from the graph, and the f of value is more the specific value at that point. Okay?
One's like what should happen and one is what is
Yes.
happening.
One is your prediction of what should happen, and one is what's actually happening at that point. Yes. Okay? Sometimes you can't actually get a limit of a graph, which is example 4 real quick here. So if I look at example 4, again, I don't expect you to know exactly how to graph all these functions on your own. I could, of course, pull up my calculator here and do this, but I'm just going to show you for the sake of time rather than flipping back and forth between the two. This function, absolute value of x over x. If I was doing this on my own and I wanted to know the limit, okay, and this is pronounced limit as x approaches 0. So this is asking me to look at the graph and check out the behavior of the graph around 0. That's what it's asking me to do. So I would grab my calculator. I would graph absolute value of x over x and just see what it looks like. And if I look at the absolute value of x over x, it would look like this. Okay, your calculator would not show you those open dots, but can I actually plug in 0, top and bottom on that equation, or would I get a problem? If I plugged in 0 here and here, what would I get? I'd get 0 over 0. Am I allowed to have 0 over 0? No, that's undefined. So that's why I have those open dots. Now, we said the limit is a prediction of the graph, right? On every other graph, we've kind of tracked in from both sides and said it's getting real close to this one number here in the middle, right? Well, officially, I'm tracking in towards what number on this one? 0, right? Because it's the limit as x approaches 0. So there's 0. If I track in towards 0 from the left, and if I track in towards 0 from the right, can I make a prediction about what those two values are both getting closer to?
0.
What y value?
No, you can't.
No, because if I track in from the left, right here, what y value does that look like it's at?
About 1.5.
Okay, we'll just say that's like, I didn't draw slash marks. That's -1. Sorry. -1, +1. All right. This one is at y equals 1.
Okay.
Are they coming towards the same y value?
No.
No. Okay, so what this means when that happens is that the limit does not exist. Okay? So when you read these off a graph, anytime you are tracking in from either side and they don't come towards the same number, the limit does not exist, and we abbreviate that DNE. Okay? So let's look at another way that that can happen. Take a look at example 5. Okay? Again, I will graph this for you so that you can kind of tell what's going on without having to grab your calculator. Okay, what function are we looking at in example 5?
Unbounded barrier.
Unbounded behavior, what's the function here?
Oh gosh, this is behavior.
1 over x squared. So if I was asking you about that, you would grab your calculator, you would graph it. You would see a graph that looks like this. Okay? All right. On that graph, what are they asking me to consider? What number? Does it exist where?
When x approaches 0.
Okay. So again, I'm looking at 0. Here's 0. How do we tell if a limit exists on a graph? We look at it coming in from the left.
Yeah.
We look at it coming in from the right. So I'm going to go ahead and track towards 0 on my graph. If you literally on your own paper have to take your fingers and trace your graph coming in from either side towards that value, do it. Okay, so I'm tracing in here and here. The last one, we could say the left side was going at -1, the right side was going at +1. Can you really say what these sides are getting closer to if they just keep going?
For y?
Mm-hmm.
0. Oh,
I mean, the only
infinity,
thing we
infinity.
could say is that it's going towards infinity, right? Is that a real number?
No.
No. So you could officially tell me this side's going towards infinity. This side's going towards infinity, yeah? Are they going towards the same number? Technically, yes, because it's infinity, but infinity is not really a number. So there's two ways of answering this question, okay? You could say, no, it doesn't exist.
I like that one.
Okay.
Done.
Okay.
No.
But why does it not exist?
Because infinity is not a real number.
Uh-huh. Because infinity doesn't exist, really. I would accept that, or you could also tell me that limit's approaching infinity. That's another way of saying it doesn't exist.
So pretty much you can't mess that one up.
Unless you tell me it's a different number, right?
Let's just say it's 6.
Yeah, let's just say it's 6.
Or when you know it's infinity, if you mess it up, you're just done.
Right.
Thanks, Dave.
So you may tell me it's infinity, but that's just another way of saying it doesn't exist. Both of those don't exist, really. Okay?
I feel you.
All right. So for the last questions here, I am going to pull up my calculator. All right? Last ones. And I'm not really going to have you do the practice stuff there. So this is the last thing we're going to talk about. Jackson, are you proving to me that you can sit there?
I'm gonna actually be really good.
I know,
it's a
until
break,
I hear
so
something talking.
It's just a break, so I need to send like a video. I'm focused in on the.
Okay. All right, I'm going to pull up a calculator real quick. All right, and I'm going to get rid of my writing. So what I'm trying to do in these examples is just show you different ways that you can see, or different graphs that you can see. Okay, so when I look at these, can I get rid of this? No? Maybe? Escape? Okay. All right, there we go. All right. So, over the next week or two, when we talk about limits, we're going to talk about different methods of doing these. And you're going to learn different methods to try. So if you were given something like question 6, does the limit as x approaches 0 of sine of 1 over x exists? Right now, you don't have a whole lot of methods. We will have other things to try, and as we walk through limits, one thing that I did last year that I didn't really get to do as much as I wanted to because we weren't in person, but I kind of have like a flow chart of thinking through this. Try this first. If that doesn't work, here's 3 other things that you can try. If those don't work, try this. So when you do limits, it's like a toolbox, and you just kind of try something. Right now, all we really know to try is the table, which is kind of a last resort if you can't see it on a graph. So when you're doing your homework, the first thing that I would want you to do is graph it. If you can tell what it's getting closer to on the graph, specifically what number, write it down and move on. If you can't, then we might have to resort to the table and plugging in some numbers, okay? So what I would do if I was trying to find the limit as x approaches 0 of sine of 1 over x is the first thing that I would do is just type it in. So I'm going to go find my sine, wherever the heck that is. I forget where that is on this one. It's somewhere else, isn't it? Let's see. Thank you. Sine. Oh, it went away. All right. I love these. Sine of 1 over x. All right. So I'm going to graph it and just see what the heck's going on with it. If I look at the graph in my calculator here, if you zoom in real close to this, this is what's called oscillating behavior. If you took physics, it's where the graph kind of goes in the middle, like the weird lines on the graph. To zoom in on this a little bit, I'm just going to zoom in closer to the middle so you can kind of see. There we go. All right. So it makes like one of those like heart rate charts that goes real quick. Okay. If it has oscillating behavior like that, okay, you can try to like scroll back and forth on that and see what the heck is going on. But in reality, it's just freaking out in the middle. Okay. It's not a very technical term, but I just say it's freaking out. Okay. If it's going up and down and up and down and up and down, if you keep zooming in on this, you will see more of that. Let me just try that one more time so you can see it. Okay. This is another good example of where a limit doesn't exist. So there, you can see it a lot better. Okay? So sometimes if it looks like it's doing that, just keep zooming out, zooming in. And now you can see what I mean by freaking out. It's just going all over the place. If it's doing something random like this, just logically, can you make a prediction about what's actually going to be happening at 0?
No.
No. So then no limit. It doesn't exist.
So if it looks crazy like that,
Yeah.
then we have permission to say no limit.
Mm-hmm.
I like that.
As long as it's crazy right around the value, right? It's crazy at 0. Therefore, yes. Now, if I ask you the limit about something further out that you can actually see, then give me a number. But if it's freaking out like that, then no. Now, it doesn't mean that every sine one is going to be freaking out like that. So it also asks about, on that same question, sine x over 5x. Okay? Again, all of these are ones that you, if you plugged in a number, you would not get a number back out. Okay? You would get 0 over 0. All right? All right, so if I plug in x over 5x. Oops, I typed that in wrong. Excuse me. Let's see if I can get that in right. Sine x over 5x. All right, let's graph this one and take a look. And I'm just going to zoom normal on this one. All right. All right, so this sine graph, it's got waves going on, but does it have that oscillating stuff in the middle? Yes? No? Maybe? What does it look like happening in the middle here?
They're meeting at 0.
It looks like it's meeting at 0. Okay? Now, if you zoom in on this, this is where you have to be careful about using your graph for some of these. Okay? Because I'm going to zoom in a couple times on this. Yes, ma'am. Oh, well, that's a good thing. Oh, let me check my mode on my calculator real quick. Okay, is your calculator in degrees or radians? Okay, you want to be in radians. And that's why it doesn't look like it. Oh, good. Let me check mine. Maybe I typed it in wrong. Sine x over 5x. Let me check my graph. What does yours look like? I wish I could see. Let me see. Maybe mine's wrong. It's a good possibility. Y equals sine x over 5x. What did I type in wrong with this? Let me try to clear mine and see. Oh my gosh, my mouse is not showing up. There we go. Sine x over, I'm typing it in right, 5x. Oh, I didn't put parentheses on the bottom. I'm a genius. All right, hold. See if we can get this in here the right way. Whoop. There it is. Oh my gosh. Okay. This is me doing really well with technology here at the beginning. All right. I think I did a little bit of typing wrong on this one. So let's take a look at the graph after I've got that typed in now. Standard. Hello? Yes. Does that look more like it? Okay, thank you for stopping me on that. All right. There we go. All right, so I got the correct graph in there. I did not put parentheses on the bottom of my equation when I typed it in. It made it all funky. It did not meet a 0. All right, let's finish this last question so we can be done. Okay? On that one, I typed it in wrong. This is what the graph actually looks like. If I tracked in towards 0 here, just take a guess at this. Okay? I've got, like, here's...
I just didn't see that hash mark.
Here's 1, here's 2. Okay, what would you guess it's getting close to in the middle?
1/8.
1/8,
No,
1 something. Okay,
1/7.
And actually, you can get the answer from the equation itself if you kind of know what you're talking about. There are rules to these. I don't want to have you memorize them. But what did we graph? Sine x over what? 5x. So if I'm thinking about that, the rule to these ones is that if you get to this and you were kind of trying to estimate it off the graph, the answer is actually the fraction found within the problem. So it's sine of how many x's? 1 over how many x's? 5. So the answer to that officially is 1/5. Okay? I'm not going to ask you to memorize those formulas. Okay? I would have taken a good estimate of this. If you just said it was something between 0 and 1, that's maybe less than a half, I would have been pretty happy. A lot of the ones that you will see like this will actually end up being whole numbers. So if it would be like sine of 5x over x would end up being 5. Sine of 6x over x would be 6 or something like that. Okay? So we're going to estimate most of these off the graph. So here